Today I'm presenting my first artifact titled Beyond Earth, an integrated aerospace logistics dashboard built entirely inside Google Colab using Python. The objective of this project is to take a massive multi-dimensional dataset and transform it into clear, actionable insights that help industries like satellite telecommunications and national defense planners analyze historical aerospace trends and risk factors. So for this project, I used a comprehensive space missions dataset from Kaggle spanning from 1957 to present day. Because raw aerospace registries are packed with different types of mixed timestamps, messy country strings, and unformatted financial statistics, a critical technical decision I made was building a robust cleaning data pipeline using pandas before generating any charts here. So in this was all the ones that I cleaned, and I handled a Latin 1 decoding error, stripped out duplicate records, chopped broken chronological rows, and programmably broke down complex data strings into a clean year axis and distinct country columns as well, as you can see here. This is all the analysis I conducted based on price and year and the country, mission outcomes, if there were success, failures, partial failures, everything here. So now moving on. I basically split my data analysis into two distinct engines, into two dashboards. So in dashboard 1, I basically wanted to see more on Plotly, and this was like a Plotly Express engine, and it focuses on temporal, financial, and geographical exploration. So there are 3 graphs into this. So the first one is a dynamic line graph mapping global launch frequencies over the last 65 years. So you can see here. And I chose this line graph specifically to highlight clear historical production peaks like the space race boom and the modern commercial rise, while completely avoiding the visual clutter of a crowded bar histogram. Second is the Plotly scatter plot here, which has the costs and the outcomes, as we can see here, success, failure, partial failure, pre-launch failures as well, and it's so that the users can instantly hover over the nodes and isolate the anomalies as well. It's color coded as well. Third one is a geographical mapping. It's the global launch infrastructure distribution over different countries. So we can even zoom in and we can move here as well. You can see Kazakhstan, India. There are 82 launches here, 1,416 launches in Russia, and 1,467 in US. So basically projects the global launch sites onto an interactive world map as pink data circles, and this visual layout instantly reveals the heavy geographical centralization of active infrastructure around the globe. Next, we're going to move on to the second dashboard here. So this has the ones from Matplotlib and Seaborn. So these are all static, and the first one is a basic box plot illustrating the national budget spreads, and a key programming choice I made was to cap the vertical axis at about 1,000 million, because this prevented multi-billion-dollar outliers from flattening our visual scale, keeping the box plot legible. Next is a Seaborn heat map here, which has the cost tabulation matrix of mission outcomes by each country. So we have the USA, Russia, Kazakhstan, etc. Failure, partial failure, pre-launch failure, and success. And it's basically I overrode the default dark mode styling by overlaying a high contrast white text grid, making the exact launch success counts like Russia's 1,323. Next is a horizontal bar chart that I did using Matplotlib, and it basically explores the ranking of the top 10 space organizations. And by choosing a horizontal layout and printing direct numerical text angles at the end of each bar, I completely eliminated vertical text clipping issues. Finally, we have the donut chart here, which is graph 7. In this, it is a vibrant pink inside Matplotlib donut chart. By applying a center masking layer over the polar coordinates, it reveals that 78% of the global aerospace fleet assets are currently retired, compared to the 21.8% that are remaining. So now we have both of the dashboards here. So in the first dashboard, we explored all the 3 that were dynamic. In the second one, where it is Matplotlib and Seaborn, we have all the ones that are static. So building a tiered dashboard environment allowed me to match specific analytical questions to exact technical strengths of each library, and I ran system test logs as well to capture any data errors early. So here it is, and I was also able to ensure visual stability by testing everyone as well. However, there are some limitations, and as we can see, the first dashboard is completely fluid and interactive. The second dashboard completely remains static, and meaning the users cannot filter corporate statistics directly onto the charts. Furthermore, the geographical map aggregates launch volumes by country rather than the individual launchpad coordinates, and in future versions I would resolve this by combining both views into a single web application using Streamlit, and expand the data pipeline to map the exact latitude and longitude coordinates of every spaceport. So thank you. So moving on to my second artifact, this is Letterbot, the core film intelligence engine. It is a fully functional, responsive web chatbot built explicitly for movie enthusiasts. So while establishing the architectural rationale for this artifact, my core objective was to move away from the traditional static database layouts, since standard conversational applications heavily rely on pre-compiled local text files or mock data sheets to stimulate interaction, which basically limits the scalability. And to solve this, my research focused on decoupled client-server web architectures and the ingestion of live data ecosystems. I chose to build a real-time data streaming pipeline that establishes a direct, secure, asynchronous handshake connection to the external REST API via the movie database API. And this ensures that every byte of information rendered on the screen is dynamically sourced, reflecting real-time global cinema telemetry. So here we can take a look at the basic interface, and we can even say hello first. So in this, we can see that it was engineered to bridge advanced functionality with the modern aesthetic standards, and the dashboard features a dark-themed visual layout created using semi-transparent glass blur effects, responsive hover states, and smooth color transitions. And in the code, we can see that this is driven by the CSS custom properties within the root selector here. And this allows for centralized maintainable style sheets. And at the very bottom here, I had engineered a continuous scrolling text marquee running on CSS keyframe animation called the text track scroll here. And this uses hardware accelerated translation across the x-axis to display real-time system diagnostics. So to ensure strict system stability, I built an explicit session control state machine. So if you look at the input doc, I designed dedicated greeting and termination button modules that route directly to a JavaScript function called execute system greeting. So that's over here. So this basically so when a user clicks this green say hello button here, say hello, it establishes a clean session configuration, and then clicking on the power down safely unmounts the session context. And this design choice prevents users from injecting empty or malicious inputs into the input element before a connection is formally established, completely eliminating broken search requests to an active external API. So now if we type in any movie, so let's type in the movie Michael here, it brings up the application. It does not simply push the raw string to a network. Instead, I engineered a highly optimized client-side text processing engine to handle linguistic classification without requiring a heavy backend server. So that is this extract intent function here that we used, and it utilizes an array of explicit regular expressions combined with boundary tags to evaluate text patterns in real time. And it basically tests the string to basically determine if the user is looking for cast, directors, or any financial metrics or the budget. So this approach is successfully, it maps inputs to 7 separate user intents without any message collision. So once the core intent is classified, a global case insensitive rejects replace method scrubs away the noise phrases, and then the clean title string is then passed into an asynchronous network controller called the fetch transformation node. So to optimize network performance, this function groups 4 concurrent API fetch sequences using a structural promise all wrapper, which is over here. And this single network flow simultaneously streams credits, core details, reviews, similar movies, etc. So here, if we press core cast, we can see the cast of any movie, and if we press any of the actors, it will show up as like a box here. So this is how the asynchronous pipeline updates the DOM dynamically based on these option clips. So when a user presses the core cast, the JavaScript engine reads the prefetched JSON matrix without executing a full page refresh, and it maps over the collection, extracts the actor profiles, and injects clean template literal strings directly onto the viewport. It's not just Bollywood movies or Hollywood movies. We can search up any movie that's available in the database, and we're able to get any film. So here I chose a popular Malayalam movie, and we can search up any actor. We can press any actor here. And if we click the recommend engine chip, the client-side system analyzes the movie's similarity index and formats the recommendation onto the chat window as clickable underlined link chips. So clicking any of these newly generated links recursively feeds the title back into our main processing engine, triggering a brand new search loop from scratch. So we can press this movie here as a recommendation, and it shows up as a completely new one, and we can even open up the posters as well. Now, a vital architectural requirement for any conversational engine is state retention, and to achieve this without complex databases, I engineered a live contextual panel called the agent context memory. So this is driven by a global JavaScript state object called the memory cache log, and what happens is that it is initialized at the start of the application scope, and whenever there's a successful search loop is completed, the application triggers the state synchronization function called the update cross session memory. And so as a result, the application tracks the user's journey in real time, and it catches the last traversed movie node and their favorite star directly onto the panel. And this creates a secure, closed-looped state environment across separate interface components during the active browser session. So to validate the structural integrity of the application, I conducted a testing table with all the issues that I had seen and expected, and the actual result that I wanted from each of the basic scenarios. I also put out a system log as well, where it also mentions all the logs and the status and the cache and the state and everything. So it even has a movie name here for the buffer target. We also have a global trends array node report here. And reflecting on this project, the engine successfully balances out multi-threaded data streaming with a highly responsive user interface, rendering dense components like profile sheets without dropping animation frames. However, a key limitation I would say is that the chatbot's reliance on exact keywords matching, causing queries to fail if a user makes a basic spelling error. So if I were to say something like Avengers, but I spelled it wrong, or something like this, maybe it would not understand it, and it would say it couldn't locate a movie path node. So it did not understand that I was actually asking for the movie Avengers, even though I spelled it wrong. So to elevate the application in the future, integrating a native natural language processing framework would allow the system to handle typos seamlessly, while also introducing local browser storage, and that would enable the chatbot to preserve conversation states across device refreshes. And that's basically it. Thank you.